welcome. This is going to be a little bit of a lecture about the quantum model. So if you're in my honors class, we've already gone over the first part of this in class, so go ahead, just skip on through what you feel comfortable already with, or you can rewatch part of this. I'll probably talk a little bit slow, so feel free to speed this up or, skip ahead if you need. But yeah, so let's just kind of talk about the quantum model. So the quantum model, this is our modern way of understanding electrons, our modern model. For electron arrangement. So kind of like this meme suggests, this is like the far superior way of talking about it. It's definitely more complicated and, harder to get our brains around. But it's a more useful model. It gives us more details than just Bohr. So that's why it tends to be what we use if you're in a more advanced chemistry setting. Because with this model, we can represent exactly where our electrons are. So like in our Bohr model, all we've talked about is like, oh, it's in shell 1, n equals 1. It's in the first inner shell, or it's in the outer shell. And we just have like, there's 8 electrons on that outer ring, that kind of thing. But like, that's just kind of a general space. Like it's kind of like just a diameter, like a distance away from the nucleus. But like, where in that area are they actually hanging out? Because it's not, in reality, they're not on this like loop that you see here. Like they're not just like circling all like this. They're actually like existing in 3D space. So this model allows us to kind of specify that. There's 4 different quantum numbers that are used in this. For honors chem, like you don't really need to know too much about the quantum numbers. It's just kind of like know that there's 4 different levels. So we're going to get more and more specific as we describe each electron. Basically what we're doing, or like the metaphor I like, is that we're giving the electron an address. We are getting more and more specific with our electron's address. So here's like an overview of our 4 numbers, or 4 like levels to this. So the first one, we have what we have in Bohr. This is all you get in Bohr. And it like about is talking about, it's like kind of just the distance from the nucleus. So just like when we've done our Bohr models, like it's going to correspond to the period of the atom. It's just our general like overview, like this is about where it's hanging out. Maybe it's n equals 1, or maybe it's n equals 2, or maybe it's n equals 3, and it's somewhere in that space. But then with these other terms, we can get a little bit more specific. So our next one, how I'm going to refer to these is these are the orbitals. So we'll see some examples of these. But the orbital, that's the main like word we're going to use. This is like the space within n where the electrons are. So like let's say n, like here, this picture, I think it's pretty good. Let's say we have n equals 2. So in this picture, like you have your 2s, you can kind of see are labeled, and your 2p are also labeled. So let's say if that was a good circle, that was n equals 2. So within n equals 2, within this distance from the nucleus, electrons can be hanging out in these different orbitals. And I think hopefully this will start to make more sense as we keep going. But the orbitals, those are just general areas within the energy shell where the electrons can be. And within each like orbital category, there are what I'm going to call suborbitals. And again, I'll clarify that in a sec. And then our final one, we can also have an electron with different amounts of spin. That's like our most specific one. So every electron in your atom is going to have a different combination of these 4 characteristics. No electron in the atom is going to be exactly the same. They're all going to be a little bit different. And so we could get super specific and be like, well, I want to talk exactly about this specific electron and it's hanging out in this specific place, and we can do that with this model. So yeah, let's talk a little bit more about how to use these. I know like conceptually, like this is very weird. It's hard for people even like at the college level to get their brains around this. So, you know, be nice to yourselves. Really focus in on like the skills that are going to come at the end of this lecture. That's more like where I want to focus getting us to. Like don't get too bogged down with the conceptual. Okay, let's see. What is our first one? So our first one, this is our principal quantum number. Again, this is N. This is like our shell from Bohr. And we're going to see this in our models as a number in front of our orbital. Okay, so just like how we could say like n equals 1, n equals 2, in Bohr, we're going to use a number to represent these. So again, this is the same thing as what you've done in Bohr. I'll show this again later, but like just to give a poorly drawn little periodic table here, pretend that, oh gosh, poorly drawn periodic table here. I'm making it worse. It's worse than when I started. That's fine. Just to kind of demonstrate, like, okay, our first row, our first period, that would be n equals 1. Second period would be n equals 2. Third period would be n equals 3, and so on. So just like when we were doing Bohr models and like you use the periodic table to tell how many shells you're going to have, same kind of concept with the first quantum number. Okay, but now it gets a little weird. So let's talk about orbitals first. So these really conceptually are the place in space where the electrons actually are. So like I'm gonna show you a bunch of different pictures of these. Like they're actual like 3D representations. Of where in space electrons most likely are. So again, within our shell, within like n equals 2, we're going to have these different areas where electrons are most likely to be, and that's what we call orbitals. We have different ones. They're represented with a letter. There's 4 types: S, P, D, and F. So these are different types of orbitals. So let's talk about them. We got the s orbital. This is our starter pack orbital. Every period, every shell is going to have an s. It's a sphere shape. And because it's a sphere, ball, there's only one orientation. Like you can rotate a ball, but it still looks the same. So there's only one orientation. And therefore, one suborbital. the whole s orbital can hold 2 electrons. Okay. Now, what do I mean by suborbital? I think it'll be clearer when we see examples with more than one suborbital. So I'll come back to that, but it's basically different versions of this orbital. And just to note here, every suborbital, every suborbital can hold 2 electrons. Okay. Okay, let's look at P. So, oh, no, thank you. No, thank you. Okay, cool. These are our P's. So again, this is a place in space where an electron probably is. So if we are, so there's just these different places in space where we are most likely to find electrons. I don't know why. Okay, sorry. I thought it was glitching out for a second. Okay, sorry. Back to this. So a p orbital, it always has this weird shape. It's like that. It's called a dumbbell is like one way we could represent it. A dumbbell shape. Are there 2 B's? There's probably 2 B's. I don't care. There are 3 suborbitals. And because each suborbital holds 2, it can hold 6 electrons total. Okay, let's talk a little bit more about this whole suborbital thing. Sorry, adjusting. Okay. So, like, what is a suborbital? Basically, what we're seeing, and again, like, this is all a little conceptual. Like, don't get too bogged down in it. For if you're an AP, like, this is more important. But for our level, like, it's kind of just an intro to this. But a suborbital means that there are multiple versions of the orbital, like multiple orientations. The same orbital type. They're all going to have the same energy. The special word, I'm not going to use this really in honors, but if you're curious, it's called degenerate. So that's just like a chem word. So if something has the same energy level, they're called degenerate orbitals. So for P, there are 3 different degenerate P orbitals. I think with the visual we do later, that'll make a little bit more sense. But okay, suborbitals, that's just same orbital type, but like different versions of it. So P has 3 different like spaces available to it. D orbital, you can see the shapes get a little bit weirder. I don't really care, like you don't need to know all these different shapes. So I guess for our purposes, I'll just say that these are weird shapes. You don't need to know their names. They're just kind of funky. But you should know that there are 5 suborbitals. These 5 different types of d orbitals we could have. And again, each suborbital holds 2, so that means that we can hold 10 electrons. Okay, F, like we don't touch F, like you will literally like, pretty much never see this. This is for the stuff way at the bottom of the periodic table that we don't really talk about. But just so you know it exists, same kind of deal. just another type of area around a nucleus. There are 7 suborbitals, so it can hold 14. Okay. Now, the cool part about quantum, like one of the things that is useful about this, you might recall when we've done our Bohr models, they don't really work for most of the periodic table. Hopefully when you've practiced those, we've said like, okay, you can only really go up to like calcium. We can't go row 4 and down. It doesn't really work anymore. Like it only works for the small guys where you can just do 2 electrons, 8 electrons. But these, when we're using the d and the f orbital, this enables us to talk about the whole table. So that is one of the reasons that this is better than Bohr. We can talk accurately about all of our elements, not just our small guys. Okay, and our final characteristic that electrons can have that's part of the quantum model is something called spin. It's just a property of electrons. It's related to their magnetic fields. It's again, very conceptually challenging. You don't need to know much about that for this class. All I really want you to know is that some electrons have spin up, so they're like going up, and some of the electrons have spin down. So they have these 2 opposite possible magnetic properties. Don't get too bogged down with it. But it's just a property of electrons. Some electrons are up, some electrons are down. So if I want to specifically talk about one electron, I should be specific of, oh, that's a down electron, or that's an up electron. So what we're going to represent these with is with up and down arrows. We'll see this more a bit later, but something like that is how I would draw them. So the first one, that's an up spin, and if I want to show a down spin, I would show it with that second one. Okay. Deep breath. I know that's like a lot of concepts. Now let's kind of focus on the actual skills that apply this. That's more what I want you to focus on. How do we actually use this as a tool? The real key is let the periodic table guide you. Like you've probably caught on with our other trends, the periodic table is beautiful. It is so magnificently designed, so useful. This is one of the many things that's useful about it. For honors, I will give you this setup, so you don't even have to memorize them. But here is how this works. So there's these different types of orbitals, right? We have s orbitals, p orbitals, d orbitals, and f orbitals. And basically, as you're like going along, like you're an atom, and the only difference between like this atom and this atom is that we've added another proton, another neutron, another electron. They all have the same structure, right? They all have the nucleus, they all have the electrons. We're just adding more of those subatomic particles. So because they're all made of the same stuff, they all follow the basic same pattern. As I add more and more to each, they should add in the same way. It's going to be this pattern. So using that concept, we can just follow along on the periodic table and use that to figure out where the electrons are. Okay? So I know it's a lot, but I think just doing examples is the only way to kind of get it to click a little bit. So just like with Bohr, you're going to see that each row has different principal numbers, different ends, going down 1, 2, 3, etc. So you can kind of see, now that we know this thing, when I represent my first orbital, it's going to be called the 1s because it's in row 1 and it's an s orbital. This one's in row 2, and it's an s orbital, so it's called the 2s orbital. So let me just finish up labeling these guys. N equals 4, n equals 5, n equals 6, and n equals 7. So just to point out a few tricky things with this. Notice as we go across here, 1s, the one n equals 1 only has s. It only has this one type of orbital, so there's only one s. In our second row, we have 2s, and we have 2p. So I've added a row, I've added a new type of orbital. Let's look at our next row. I have 3s, 3p, and then here's our 3d. So that's where it gets a little bit confusing because it does have this kind of staggered pattern. 3s, 3p, 4s, 3d, 4p. I know it's a little weird. Basically, it's just kind of showing the energy levels of these different electrons. Again, for honors, don't need to harp on it too much. It really is just showing that for each n, as we go up in n, we're adding one new type of orbital. As we go up in n, we're adding a new type of orbital. And just because of how the electrons work, we're going to have like this kind of staggered pattern. So just add this label to your periodic table. The ones in the middle are transition metals. Notice that all of them are actually going to be n-1. So this one's in row 4, but it's the 3d. N equals 5, the 4d, and so on. These are our F blocks. Again, we do not use them, but here they are. You might notice that these are n-2, but again, for this class, I won't ask you about these. Even for AP, they don't really come up. Okay. So I'll show you how to use this in a second. Hopefully that'll help click it a little bit more. But the periodic table is arranged to show us where in the atom each new electron is going to go. So as I move across, as I get this one to this one to this one and add more and more electrons, I can tell which orbital to add it in based on the periodic table. But I will show you what I mean by that in a second. So electron configurations. This is our first big skill that we got to get down. It's how we're going to represent where all the electrons are in our atom using this quantum model. Okay, don't know why she's glitching out. That's fine. So just like with Bohr, what I'm going to have you do is start at your lowest energy level. AKA n equals 1, you're going to just start at the top, fill in your low energy ones, the 1s, then the 2s, then 2p. Just like Bohr when we did the first ring, then the outer rings. Always start with your lowest energy level. And here's the big tip for you. Really let the periodic table guide you. Like, it is set up in a way where you can, if you get used to this pattern and you get used to how to do this, you really just follow the periodic table and are able to create these based on that. So when we create an electron configuration, you're going to make a series of things that look kind of like this. There's always going to be a big letter, or sorry, a big number in front, a letter, and a little exponent. So what do all these things mean? The number in front, that is your energy level. Your principal quantum number, your n. The letter is the orbital. So the 2s is within energy level 2. it's the s within that area. So 2s is the orbital within energy level 2. And then this part is important. The exponent, that is the number of electrons in that orbital. So what this is communicating to me right now is that in the 2s orbital, in that specific area of space, there are 2 electrons in that orbital. So that's what we're communicating. So like imagine that there's a little area around the nucleus. Within energy level 2, there's this little sphere. And what I know from 2s2 is that there's 2 electrons in that space. And the 2s can hold 2 electrons because it's an s orbital, so that's a full orbital. Sorry, I don't know if I'm rambling a little bit, but again, it's something that takes repetition. Just practice and get used to the patterns and you'll be okay with this skill. So expanded electron configuration. This is how I would represent every single electron in an atom. Okay, so let me talk you through how I would do this, and you can copy it down on your notes. So the goal for this one was to find the electron configuration for carbon. So first step, find carbon on your periodic table. Wow, my iPad is glitching out. Okay, let's get through this one. Okay, so find carbon on your periodic table. There she is. So our goal is to go through and represent all of the electrons, all 6 electrons in carbon, and what orbitals they're actually in. So how I'm going to do this is you're going to start at the top, start at your energy level 1, and you're just going to move across the periodic table and write down all of the electrons you tick off. So our first orbital that we're going to fill, we're in n equals 1, and from your map, you know that this is the s area. So you're filling the 1s orbital right now. The 1s orbital. And if we count across, I have 1, 2 electrons in my 1s orbital. And I represent it like that. So you figure out what orbital you're filling. In this case, the 1s, because we're filling the s block of our first row. And there's 2 electrons, so just counting across the row, I went and got to the end of the 1s, the end of my blue outlined ones. I got to the end of that. I'm not at carbon yet, so that means I've filled that one. I've counted 1, 2 electrons there, and that's why I put a 2 there. Then we move on to our next one. So we're filling the 2, because we're in row 2, and we're going to fill the s first. So here's my 2s, and I count 1, 2 electrons in that area. 2s, 2. So I've filled up my 2s. I've counted across that blue area, but I haven't gone to carbon yet, so I have to go to my next orbital. I'm still in n equals 2, so I'm in my 2, but now I'm going over to p, so I'm at 2p, and within the 2p, I have 1, 2 electrons. I've reached my goal, I've reached carbon, so that's all I'm going to count. So carbon has 2p with 2 electrons in it. Okay? I know this is a lot of jargon at once. but hopefully you see how I did that. So let's do another one. Again, you're just going to start at the top corner and count across. Oh gosh. Okay. I'm going to erase this one. Or not. Cool. Okay. Your next example is asking for titanium. So first step, let's find that on the periodic table, Ti. And again, we're going to start at our top corner, our lowest energy level, the 1s. And we're going to count across until we get to Ti, to titanium. So we have 1, 2 in our 1s. So it's 1s2. Then I go to my next row, I'm in the 2s. And I have 1, 2 electrons there. I have to go over to my 2p and count across 1, 2, 3, 4, 5, 6. Still haven't gotten to titanium, so that's 2p6. My next orbital is the 3s, and I have 1, 2. Then I have to move on to my 3p and count across 1, 2, 3, 4, 5, 6. Next row, I have my 4s, and there's 1, 2 here. Now here's the tricky part. Again, if you're in honors chem, I'll give you this map, so you remember that this section is n-1. So what I'm filling here as I cross off these, what I'm actually filling is my 3d. So down here, we're filling our 3d orbital. Oh, okay, cool. 3d. And we're going to fill that with 1, 2 electrons. Okay. So yeah, I'm going to pause this here just so I don't run out of time, and I'll pick back up. Okay, welcome back. Hopefully this will work a little bit better now. Okay, so just to recap, we've filled in our electron configurations for these two different ones. So just to clarify again, why our 4s comes before our 3d. This fills first. The actual reason is because it has a lower energy level. For honors, that's not that significant. So for the sake of making it a little bit simpler, you can think of it as we fill the 4s, because the 4s, like as I was moving along the periodic table, comes first. Just a little bit of vocab stuff. Again, for honors, I won't really harp on this too much, but something good to know, especially if you're deciding to do more advanced chemistry in the future. That last orbital you fill is the one with the highest energy. So again, ingenious design of the periodic table, as you just follow it and go along, you're filling in order of energy. So that last one you filled, this one in this case, has the highest energy. Again, for CP or for honors, I won't ask you that, but just so you know, that one's our one with the highest energy. The orbital with the largest principal quantum number are N. Those are our valence shells. So the electrons in those orbitals are the valence electrons. So for this one, because number 4 is our biggest N, our biggest number, this 4s, that is our valence electrons. So there's 2 valence electrons. Okay. All right. So that's annoying, right? Going through the whole thing and labeling every single electron. So there's a little shortcut. So here is our nice little shortcut. So if I ask you for a noble gas configuration, that means that you get to do less work. So let's go back to our periodic tables. So let's do magnesium first. Okay. So if our goal is to make it for magnesium, just like we did before, let's orient ourselves. Let's find magnesium. It's right here. Okay, but the noble gas configuration. So reminder, these are your noble gases. These are your noble gases. So when I say noble gas configuration, what you're gonna do is you're gonna find the noble gas before your goal. So magnesium's here, and the noble gas that comes before it is neon. Do you see that? So it's the one that comes before it. So argon comes after it, neon comes before it. So what you can do is in brackets, you write Ne. And what that does is say, again, as we were seeing with the other ones, they follow this pattern. All of the atoms have the same base structure. We're just adding more and more electrons. So it can be said that up to this, here, let me use a different color. Up to this point, up to neon, magnesium has the same configuration as neon. I went through my 1s, I went through my 2s, I went through my 2p, and I got to neon. So I can just kind of cut out those first 2 rows, cut out everything up to neon, and just start here. So I've cut out everything up to neon, and now I just have to count everything past neon. So after neon, I'm in the 3s. And to get to magnesium, I have 1, 2 electrons. So that would be my noble gas configuration for magnesium. A lot less writing, right? So just look at the noble gas before your desired element, put it in brackets, and then start at the beginning of the row. Okay, so let's try another one. Next one is for chlorine. So if I want to do chlorine, and again, I'm going to look for my goal. So my goal here is chlorine, and I'm going to pick the noble gas that comes before it. So the one that comes before it is going to be neon. Do you see that? So the one before chlorine on the periodic table. So let's start that. Chlorine is going to be, up to neon. So up to this point, it's the same as neon. And then we just start at the beginning of the row. So starting at the row after neon, I have 3S. Oh my goodness. I have my 3S, and I have 1, 2 electrons in the 3S. And then I move over to my 3P, and I have 1, 2, 3, 4, 5. So 5 in the 3P. Now, what it says on your paper, you might notice, is that this would be if it was neutral chlorine, right? Just normal chlorine. But as it says on your paper, we actually want to get our electron configuration for the chlorine ion. So chlorine -1. So think to yourself, what does it mean that we have a -1? Think to yourself. It means we have 1 extra electron. And so I'm going to add my extra electron to my valence. I'm going to add my electron to my valence. So because I have an extra electron, it's actually 3s2 3p6. So 1 extra electron in your valence shell. Okay. So hopefully we got that written down in our space. Here, why not? I'll just summarize it. So our NE, you can just speed through this if you don't need it. And again, that extra electron is being put in your valence. Any ion stuff is always with your valence electron. Or sorry, your valence shell. Okay. Okay, so that's skill number 1, electron configurations. Just kind of showing, okay, I have these different orbitals with these different names, the 1s, the 3s, whatever, and I have these different amounts of electrons in it represented by these exponents. But our next skill that is helpful is making something called an orbital diagram. So this is a visual representation of your electron configuration. Basically, we're going to show each electron in its suborbital. Okay, so just to front load a few terms, for honors, I don't care if you know these names. It's just kind of background, like how we make these. if you are choosing to do AP or some more advanced thing, you do need to know the actual names. So here's the different things that are going to help us with this. First is called the alpha principle. Electrons, and I know they have fancy names, but you actually already know this. Electrons fill from lowest energy to highest energy. So you already know that one, you just didn't know the name. Just like with Bohr, just like with our electron configurations, you start at your n equals 1, your 1s, and then go up. Okay. Now these ones are going to help us with our actual little pictures. Hund's rule. Electrons fill, let's say electrons individually fill each suborbital before electrons begin to pair up. So you'll see this in action in a second. I think it will make more sense. But electrons, remember, each electron has a negative charge. Opposites attract, same charges repel. So electrons like their space. They want to spread out if they can. So if there's multiple suborbitals available, they're going to spread out first, and then if they have to hang out together, they will. But if they can spread out, they're happier with that. They want to be away from those other negative charges. Okay, and finally, Pauli exclusion principle. I mentioned this a little bit earlier, but this is the concept that no electron can have the exact same address. No electron is going to have the exact same combination of those 4 levels, those 4 quantum numbers I talked about earlier. So what that kind of comes down to, what you're going to see, is that when I start pairing up my electrons, when I put them in the same space, in the same suborbital, we'll have opposite spins. So one is going to be up and one is going to be down. I know, lots of concepts, lots of words. Let's see it in action. I think that'll help. So I kind of wrote out what my process is with this here. So you can come back to these kind of steps to kind of help you out. But let's just work through these ones. I messed up my spacing on here, but hopefully you have better space on your paper. So how I like to do this, I like to represent these and be able to show the amount of energy that each suborbital has. So I make a little axis for myself. I'm going to line these up like on top of each other based on their energy. So just like we have with all our other stuff, we're going to start with our lowest energy orbital. So starting with my 1s, and I'm going to label it. So 1s. And then I make a line, a space, to represent each suborbital. So you might remember from our notes earlier, if it is an s orbital, by definition, it has one suborbital. There's only one space. So when we say draw the suborbitals, this is what I mean. So if it's an s, you have one spot. And then we're going to represent all of our electrons in that orbital, filling each suborbital, and then only if I fill up all of them, I'll go back and add pairs. So let's see how this works as I go. So our first orbital, our 1s, has 2 electrons in it. So in my little space, I'm going to write 1 electron. And if I had more space, I would spread them out, but I don't. So 1 electron, no more suborbitals to fill. So I put my second electron in that same suborbital, but I make it a spin down. Make them different. 1 up, 1 down. They have to be unique. Okay. And like we saw when we were doing our electron configuration, the way this is written is in order of energy. So my next energy is going to be the 2s. So I just like to stack that up on top. I kind of like to align my different letters. So the 2s, sorry for those weird lines. The 2s, it's an s again, so I make only 1 suborbital, only 1 spot. There are 2 electrons in it. So I'm going to show my 1 electron. There's no more suborbitals, so I show my second electron as a spin down. Okay. Okay. And then if you're in honors, it really doesn't matter if you kind of mess up, if you don't align these perfectly the way I'm doing them. This is just how I like to show it. The 2p has more energy, so I'm going to draw it a little bit higher up. But because it's a p, I like to move it a little bit to the right just to show that it's a different type of orbital. P orbitals, by definition, what we covered earlier, have 3 suborbitals. So there's 3 spaces within our p where the electrons can go. I have 2 electrons in this orbital. Hund's rule, I'm going to spread them out if I can. So first electron, second electron. If you did this, that would be wrong. They do not want to be next to each other. That is not correct. If there are available suborbitals, they will spread out. So that is the correct orbital diagram. Okay, let's try another one. So a little bit beefier of one. Again, I like to set up a little energy axis. Okay. Can we function, please? Cool. Okay, so starting with my 1s at the bottom, 1 space because it is an s orbital. My 2 electrons. Spin up, no place to put my second one, so I put a spin down. 2s, stack it up to show that it has more energy. 1 space because it's an s. 2 electrons, so I go up spin, down spin. That is my 2 electrons. 2p, a little bit higher energy. And the p, because it's a p, has 3 suborbitals. And even if there's 6, practice doing the Hund's rule. They have to spread out. So I will fill these as 1, 2, 3, 4, 5, 6. So I only paired them up once I ran out of suborbitals. 3s. Again, a little bit higher energy. 2 electrons, 1, 2. 3p with 3 suborbitals. 6 electrons, 1, 2, 3, 4, 5, 6. 4s, a little bit more energy. It's an s, so I'm putting it on my left side. 2 electrons, 1, 2. And this is where it gets a little bit more tricky when you're dealing with the d orbitals. If you're in honors, don't stress about this too much. Again, if you don't align these the way that I'm doing it, I don't care that much, as long as you show your up and down spin correctly and like that there's the right amount of electrons in each spot, that's fine. But how I would do this, if you want to do it correctly, I tend to kind of put my things with the same energy level in a diagonal. So my 3D I'm going to put up here, a little bit more energy than my 4s. 5 suborbitals because it is a D. 2 electrons, 1, 2. Again, spreading those out, they should not be paired. Okay. So hopefully that kind of clarified these two different skills, making electron configurations and making your orbital diagrams. If you're in honors, please try these practice problems now, see if you kind of got that down. There's more resources posted on Canvas if you want to hear other people go over this, and I'll try to do some practice problems in class as well. But yeah, thank you for your attention, and just reach out to me if you have any questions. Good luck on those problems. And now I'm actually ending it.